There have been recent advancements in computer vision due to deep learning. These have opened up a lot of opportunities in real-world application. The topic of our research in computer vision is grab detection. Grab detection is the detection of hands grasping objects in an image or video. Some possible applications of grab detection is in retail and security. Some difficulties encountered in grab detection is occlusions. Occlusions occur when an object is partially hidden by another object in front of it. Hands and objects can appear very differently depending on the grasp on the person and on other variables. There's a scarcity of data when dealing with hand-object interactions. We propose an object detection network using deep learning techniques that predicts in real time if a video contains a hand grabbing an object. We also introduced an annotated hand grasping dataset containing RGB images of hands grasping different object geometries taken from different viewing angles. So our project can be split into two parts: the dataset generation and grab detection. So in dataset generation, we capture videos of grasping hands from multiple angles. Then we acquire the image frames from the videos. After this, we annotate these images with bounding boxes and labels. With this annotated dataset, we get to train the YOLO V4 object detector to detect grasping hands in images or videos. Let us now move on to related works. Fix et al. Introduced a hand grasp type taxonomy composed of 17 different grasp types. Narasimhaswamy et al. Extends mask RCNN to the problem of hand detection and segmentation. G et al. Uses deep learning models to estimate hand key points from RGB images and recreates the hand into a 3D mesh model. Kai et al. Then extends hand detection by training an object detector that can detect hands and then classify them into hand grasp types based on the taxonomy developed by FAIS. Kai et al. Found out that certain object attributes, such as object shape and rigidity, are closely correlated to certain hand grasp types. G et al. Created a synthetic hand dataset by rigging a 3D hand model with joints. This can then be configured to make certain hand configurations and poses. Kai et al. Then annotated the Jutea dataset, so we differentiate our work by simplifying previous systems. So instead, we propose to create a grab detection network that directly detects the grasping hands. In line with this, we decided to be training on images taken from various viewing angles. Let's move on to the problem statement and objectives. There are no previous studies that focus on grab detection specifically. So to address this, we propose to implement an object detection network trained to detect hands that are grasping objects in images and videos in real time. So another significant problem in hand-object related research is a lack of data. So our goal is to provide a comprehensive dataset that includes images of hands grasping objects captured in a variety of environments and angles. So now let's move on to the methodology. We attempted to create our own synthetic dataset to easily produce large amounts of data in a shorter amount of time. So we attempted to do this using Unreal Engine 4. The user is able to control the virtual hand to grab the virtual objects. Unfortunately, due to the global pandemic, we were unable to continue generating synthetic dataset. From the work of Kai et al., we get the notion that certain object attributes have a strong correlation with which hand grasp types are used to hold. The same object attributes were used so that the users will be able to exhibit similar grasp type variations. Neural networks have a hard time when presented with images taken from angles that they aren't trained with. So to solve this, we need to train the object detector with images taken from various angles. We recorded 22 videos lasting 1 to 5 minutes each. So images were extracted from the videos by sampling them.
We generated 5,622 images for training,
1,800 for evaluation. So to evaluate how our system is able to generalize, we conducted experiments on a public human grasping dataset called the UE grasp dataset. So object detectors are mainly composed of 3 parts: the backbone, the neck, and the head. The backbone of an object detection network is usually an image classifier trained on ImageNet. So this is used as a feature extractor of the input image. These feature maps are then fed into the neck. The neck is usually used to aggregate feature maps from different stages. So the head is used to predict bounding boxes and classes of the objects in the image. These are the criteria that we used in selecting the object detection architecture. YOLO V4 is able to satisfy our criteria and also achieve the highest mean average position of 43% in the Amascoco dataset. CSP Darknet 53 is the backbone used for YOLO v4. It is done by applying cross-stage partial connections on each block of the Darknet 53. Spatial pyramid pooling is used due to it increasing the receptive field and separating out the most significant context features. The modified pan is used as the method for parameter aggregation from different backbone levels for different detector levels. YOLO v3 is used as YOLO v4's head because it has good real-time performance of inference and has high accuracy when compared to modern detectors. In the implementation of our network, we closely follow the approach of Alexei AP on GitHub. Training the object detector was done incrementally using a train then evaluate methodology.
We evaluate the object detector performance on two standard metrics, namely average precision and average frames per second. Average precision, or AP, is regarded as the standard metric in object detector performance. We measure average precision at intersection over union, or IOU, of 0.5. For the inference speed metric, we use average FPS. We evaluate the performance of our object detector on the evaluation set of the GRAB dataset and on a public grasping dataset called the UT-GRASP dataset. Our GRAB detector achieves an average precision of 88.01% in the evaluation set of the GRAB dataset. This relatively high average precision can be attributed to 1. Being trained on a relatively large dataset, 2. The dataset having images taken from different viewing angles, and 3. The object detection architecture and techniques used by YOLO v4. As can be seen in the figure, high average precision can be observed on all viewing angles, except for the case of the right viewing angle. We believe this degradation in performance of nearly 15% from the mean is due to two important reasons. One reason is that this particular viewing angle is represented by the least amount of examples in the training data. Another reason is that viewing from the right side viewing angle means that in most cases, the camera will be viewing the back of the hand. The back of the hand is usually seen as a flat surface which presents very few visual features. As can be seen in the table, there is a performance degradation of around 12.5% in average precision. Three observations can be made that may have led to the degradation in performance. 1. The UT-GRASP dataset is only taken from the egocentric point of view, and training images in that particular viewing angle is limited. 2. There is a noticeable visual difference in skin tone of the persons in the dataset, the object being grasped, and the environments where the videos were taken. And 3. The resolution size of the images are different. It is important to note, however, that a 12.5% degradation in a cross-dataset study is a relatively small gap in performance. This indicates that our object detector can generalize well to new images and videos. Next, we show the inference speed performance of our GRAB detector. As can be seen in the table, our object detector can perform in real time. This makes it viable to be used in establishments for security and retail. Next, we compare the performance of our object detector to other modern object detection architectures. We evaluate these object detectors in average precision in our GRAB dataset and UT-GRASP dataset. Experiment results show that our object detector achieves similar performance to other object detector architectures when evaluated on the UT-GRASP dataset, which is limited only to images from the egocentric viewing angle. However, results also show that our object detector significantly outperforms all other object detector architectures in the GRAB dataset, which is composed of images taken from multiple viewing angles. This demonstrates the robustness of our object detector to images and videos taken from different angles. It can be observed that our object detector outperforms all other object detectors. To conclude, in this research, we created a method for the real-time detection of hands grasping objects in images and videos. We have also generated and annotated a new dataset of images of grasping hands taken from multiple angles. This dataset can be used for training and evaluating a future hand grasp detector. Our GRAB detector can process images and videos in real time on videos with a resolution of up to 1920 by 1080 pixels. This makes it viable to be used in most establishments with CCTV cameras. Moving on to recommendations for future work, one avenue is in the automation of creating a dataset. As discussed in related works, deep learning models perform better when they are trained with significantly more data. A synthetic dataset of virtual images is a cost-effective way to generate more data. We suggest the use of semi-automatic annotation by using our GRAB detection network in labeling more images and videos. This method will significantly quicken the creation of a manually gathered dataset. Thank you for watching.